Hello, welcome to Chemistry Travels. So, in the past three videos, we dealt with two major monosaccharides, that was glucose and fructose. Now, we move on to polysaccharides. So, in the very first part of carbohydrates, we saw what polysaccharides are. They were a classification of carbohydrates which on hydrolysis gave rise to large number of monosaccharides. So we can say that these polyhydrides are some hundreds or thousands of monosaccharides that are joined together by some sort of linkage called the glycosidic linkage. Okay, and in this video, we are going to deal with two important polysaccharides, one being starch and other is cellulose. Okay, so starch, if you look into the physical properties of starch, we can find that starch is a white amorphous substance that do not have any taste or smell. And to talk about its solubility, we can say that starch is insoluble in water. And if you add it to boiling water, it forms a colloidal suspension. A translucent colloidal suspension is being formed. And if you try to boil it with some dilute acids, this starch would initially give rise to dextrin, which further gives rise to maltose, and finally glucose is formed. So the ultimate product is glucose or after acidic hydrolysis of starch. And if you use some enzymes like enzyme diastase for the hydrolysis, then starch would give rise to maltose. And if you treat starch with some iodine solution, you can find that a blue color is formed. The solution turns blue in color, and this blue color disappears on heating, and if you cool the solution, it will reappear. And this is definitely one of the tests that we do for in our labs, right? And also, if you treat starch with either the Phelan solution or the Tollens reagent, you can see that it does no reaction takes place. You do not get any silver mirror or that red precipitate. So you can easily say that this is the non-reducing carbohydrate. Starch is a non-reducing carbohydrate. Okay. Now, if you look into the structure of starch, we can see that it consists of two major portions. One is the amylose, which is 10 to 20% of the structure, and we have amylopectin that accounts for 80 to 90% of the structure. And amylose is water soluble fraction in starch, and it is composed of alpha D glucose units. It's a linear polymer that consists of around 200 to 1000 alpha D glucose units that are linked together by alpha glycosidic linkage. And the linkage occurs between the first carbon of one glucose unit and the fourth carbon of the next glucose unit. That's how the linkage goes. We have different glucose units arranged in a straight line, and between the first carbon of one glucose unit and the fourth carbon of the adjacent glucose unit, a linkage occurs. This is the alpha glycosidic linkage in amylose. And also, when we saw the properties of starch, we saw that with iodine water or iodine solution, starch would give rise to blue color. And it is actually this amylose part of the structure that is responsible for the blue color of iodine. Blue color with iodine solution. Okay. So, to talk about the structure, if you look here, we can see that there are two glucose units. Two individual glucose units are kept one next to the other. Now, where does this linkage take place? The linkage occurs between the first carbon of the first glucose unit, and the fourth carbon of the second glucose unit. That is between this carbon, this group, and between this group of this carbon of the second glucose unit. A linkage happens like this between at this position, and what do we get? The product is the amylose part of starch, and that is something like this. Between the first one and the fourth one of the next, a linkage was formed. They were individual OH groups. Now a bond is formed, a glycosidic bond is formed, and this is the alpha 1,4 glycosidic linkage that occurs in amylose, and this keeps on repeating. Again one more is formed, again one more will be formed, and this keeps on repeating, and around 200 to 1000 glucose units keep repeating like this, forming the whole amylose chain. Okay. Next we have the second part, which is amylopectin, which is 80 to 90%. So in comparison to amylose, this amylopectin part is water insoluble. This part of starch is water insoluble, and instead of being a linear polymer, this is a highly branched polymer. It's a branch polymer, and this has a large number of short chains of 25 to 30 D-glucose units. There are large, like 25 to 30 glucose units. Then, like that, so many chains of such 25 to 30 D-glucose, alpha D-glucose units are together. They link together. They form branches leading to the whole amylopectin. And here also we have alpha linkages, and two types of alpha linkages are there in amylopectin. The first one is the same as amylose part, that is C1 between the first carbon and between the fourth carbon there is alpha 1,4 linkage that is there. Also, for forming the branches, the next type of linkage is there, that is also an alpha linkage, which is between the first carbon of a terminal glucose in a chain. In one chain, the terminal glucose, that one's first carbon, and in another chain, the sixth carbon of the second glucose, C1 of the terminal glucose in a chain, and C6 of other glucose unit in the next chain. Between two chains, a alpha 1,6 linkage will be formed, which will be seen in the next slide. We'll see the structure. And also the difference is here, when you treat with iodine water, it was the amylose part that gave rise to the blue color, whereas amylopectin would actually give rise to a reddish brown color if you treat with iodine water. Okay. So now let's look into the structure, chemical structure. So here I have drawn two chains of amylose. The first one, this is an amylose chain which has glucose units joined together by the alpha 1,4 glycosidic linkage. Similarly, we have one more chain at the bottom. This one also is a continuous linear polymer of alpha D glucose with 1,4 glycosidic linkage. So these two are two individual or independent amylose chains. Now what happens is, between the C1 of a terminal glucose unit in a chain, in this first chain, this is the terminal, the ending glucose unit. There are so many glucose units and the end glucose unit is this one. And between C1 of that and C6 of another chain, from the second second amylose chain, I consider any one glucose unit. I consider this middle glucose unit in this example. So C6 of that is that CH2 which I have here. This is the C6 in that, right? So between this terminal C1 of my first amylose chain and the C6 of the second amylose chain, they two link. A linkage occurs like this. And what happens is, we get this branched product. That is, we have this linear chain, we have one more linear chain. Now there is a branching which leads to the alpha 1,6 glycosidic linkage, and this whole thing is my amylopectin. Okay. Next we come to cellulose. So cellulose, it is the main structural part of trees and plants, like it is mainly present in the cell wall of plants, trees and all. Okay. And physically it's a white amorphous solid. This is also insoluble. This is unlike starch, it is insoluble in water. Starch is water soluble, this is water insoluble. But it is soluble in this Schweizer's reagent, which is ammoniacal copper hydroxide solution. Okay, treatment of copper hydroxide with ammonia would give rise to a complex, which is the Schweizer's reagent. Okay. And if you hydrolyze it with dilute acids, this would give rise to glucose. And the final product, the complete hydrolysis, will give rise to D-glucose. But if it's an incomplete hydrolysis, then cellobiose is a product that is formed. Okay. And if you consider cattle, cows, goats and all, they have some digestive enzymes within their body that are capable of hydrolyzing the cellulose to glucose. So they can feed on cellulose. That is why you can see cows and all, they feed on plants, grass. They can easily digest the cellulose by hydrolyzing it into glucose. But if you consider mammals like humans, we lack this necessary enzyme in our digestive tract, and therefore we can't directly use cellulose as our foodstuff. Okay. And if you talk about the structure of cellulose, this is also similar to the amylose part. This is also something like that, a straight chain polysaccharides. It's a linear polymer. and it is composed of D-glucose units. Similar to amylose and mylopectin, this also has D-glucose unit. And unlike the previous starch structure, this has a beta-glycosidic linkage. Instead of an alpha-glycosidic linkage that is present in starch, cellulose has a beta-glycosidic linkage between the first carbon of one glucose unit and the fourth carbon of the next glucose unit. Similarly, you have several glucose units that are placed one next to the other, and between the C1 of one glucose unit and between the C4 of the next glucose unit, we have a beta linkage that causes the linear chain to be formed. And in the cellulose, the number of glucose, the D-glucose units can range from 300 to 2500. Also, there are OH groups, right? In cellulose, like in the glucose unit structures, we'll have several OH groups. As we all know, in the glucose structure, several OH is there. And these OH groups also, between the edges and chains, they can form hydrogen bonding. Clear? So, this is the structure of cellulose. Here, we have one glucose, and the difference is the other glucose is like the reverse or rotated version, a 180-degree rotated version. The molecule, the glucose, if I had it like this, the second one will have it like this. It's rotated. So whatever is on the top goes now to the bottom. It comes. Okay. It was a 180-degree rotated molecule. It's like one glucose like this, another glucose like this. Then and a linkage is formed between the first carbon of the first glucose and the fourth carbon of the reverse glucose. Right. This is the beta linkage, and a beta linkage is formed. This is how it is placed. One straight, one reverse. Again straight, again reverse. So this keeps on going, and in between first and fourth, in between linkages are formed, and these are the beta 1,4 glycosidic linkage that is found in cellulose. Okay. Okay, so now we move on to the last part of today's video, that is some important reactions of cellulose. And these reactions are of great importance for us because these reactions can be used to produce artificial silk, or commonly called as rayon, from cellulose. Okay, so the first reaction is treatment of cellulose with nitric acid and sulfuric acid. When you treat it with a mixture of these two acids, cellulose converts to nitrocellulose. And from the name, nitrocellulose sounds like a nitro compound, but no, rather it is a nitrate ester that is being formed. If you look into the structure of cellulose, we see that they have glucose units, and these glucose units have OH groups, and every glucose unit has three OH groups that are in the free form. And these three OH groups can react with these acids and get converted to the nitrate esters. Okay. And if you're treating cellulose with a concentrated acid mixture of HNO3 and H2SO4, you will get cellulose trinitrate, which is gun cotton. That is, all the three OH groups get converted. But if you're treating with a dilute solution mixture of HNO3 and H2SO4, cellulose would get converted to either a mononitrocellulose or a dinitrocellulose, where only either one or two OH groups react and not all the three. The second reaction is the treatment of cellulose with acetic acid, and in presence of H2SO4, this acetic acid reacts with cellulose, giving rise to cellulose triacetate. Another reaction is the treatment of cellulose, digesting cellulose with NaOH solution and then treating or then passing carbon disulfide to the solution. So what product is formed is sodium cellulose xanthate. Finally, if you treat cellulose with you're agitating cellulose with 20% of aqueous NaOH solution, cellulose, it will swell and get converted to an unstable form, which is sodium cellulose. And this is a highly reactive form or an unstable form that readily decomposes back to cellulose. And that decomposed cellulose, the final product, that unstable part that we get, that cellulose properties are not same as that of the initial cellulose. Its physical properties are slightly different, and this unstable form is also called as mercerized cellulose. Okay, so using these reactions, we can actually convert cellulose to artificial silk or rayon. So That's it for today's video where we learned about two major polysaccharides which were starch and cellulose, their properties, structures and reactions. Hope you understood the concept. Thank you.